First of all, I must sincerely
Recording in progress.
apologize that I am not there. I just got the stupid flu, and then I got COVID on top of it. So I'm better now, but it could in fact be that I will ask you in the middle, maybe for a minute or so, just to get some water. Um, the I would really have loved to be there. It's a famous school. I've heard a lot about. Lots of very smart former students of the school went on to do terrific careers. And in addition, the weather in Germany is so dreadful at the moment that I envy you very much. So if you have questions in the meantime during this course, you just need to yell. I have essentially no visual feedback, but please go for it. Doesn't matter how far I'm getting here with this. Good. We will be talking about strong correlations. And first and foremost, one wants to talk about the individuals who made all of this fun because one could collaborate with them. There was Ilya Esterlis, now a faculty at Wisconsin, Konrad Skalm, who is from Leiden by training, a particle and string theorist, Gian Andrea and Veronica, graduate students in Karlsruhe, and Davide is a postdoc there. And we got money from some people. What I want to discuss in this lecture, and this will also go all the way up to next lecture, is something that has to do with an interesting question of the role of randomness in correlated materials. Randomness for all kinds of different reasons, and we want to see whether we can, on the one hand, describe it properly, or whether we can use insights, tools, and intellectual concepts that are born originally, in fact, out of the theory of random systems to go to some extent beyond this. This will play a big part in tomorrow's lecture. So just to give you an idea, this is a nice set of plots I got from a popular article here. These are all 100 lines with very different ways in which they have been generated. The first one is obvious. It's just like a clock. They have a periodic arrangement. We can see this with our eye. It's certainly not something we would call random. Then we have something that's generated with a Poisson process. And it looks clearly distinct, and then the jiggled one is something in between. That's the periodic version, and where it is shifted either up or down a tiny little bit with some small Gaussian weight. So we can see that something is random and something is not random, right? It's completely obvious, and these are sharply and conceptually deep, distinct phenomena. We don't need to go further into details unless one looks at phenomena, and this was done in the 1950s and 60s. For example, these are the experimentally observed 100 lowest eigenstates of the nuclei of the nucleus erbium 166. So it is not, this is clearly, it's a fixed nuclei. There's nothing where we would say this has to be random. But on the other hand, of course, when you look at this, it looks rather random to me than similar to what we saw in the periodic picture. And it gets more interesting, of course, when you look at the eigenvalues of, these are the middle 100 eigenvalues of a 300 times 300 random matrix with real entries, so symmetric. Now the eigenvalue problem is clearly a genuinely random problem. These are randomly chosen indices of the matrix, while the erbium eigenstates are obviously non-random. You can also do something even more fun. You take, you want to numerically check the Riemann hypothesis. The Riemann zeta function is supposed to have zeros along the imaginary axis. Sorry, at the real part of minus a half. If you wait for the 10 to the 22 first zeros and then look at the larger zeros, then you get what's thrown here as the zeta zeros. Which ones? This is not a random process. It's a well-defined formula. It's Riemann zeta function we all know. And these are interesting analogies between these three lines that we've seen here in the middle, erbium eigenvalues and zeros, even though they have very, very different origin. We can go further. The one that I like in this article here cited is the location of bridges of I-85 if you're starting north somewhere in the US, and then you see there seems to be also something that you could call a level repulsion, and so forth and so on. What's important for us here is in particular the discussion of these three phenomena that goes back, of course, to Eugene Wigner and his proposal that nuclear spectra are characterized by random matrices, by Freeman Dyson and by Hugh Montgomery, who is a number theorist who, together with Dyson, established the relationship between zeta zeros and random matrices. So what does it mean? Well, what is not random may appear very random. Here again, this is the distribution of, say, the level distances on the one hand from the erbium spectra, and on the other hand, is generated with the random matrix ensemble. Here we see again the zeta zeros. There's no proof, I believe, that exists analytically that these two lines, the random matrix distribution function of symmetric matrices and the Riemann zeta zeros, are indeed asymptotically the same, or I think this is what Montgomery proved, but it is under mathematicians something that is not completely considered a proof, but I mean, I'm personally convinced. So this is just as an introduction to get a sense that it's not always obvious that whether or not something is random. If you, of course, look at a given material, then very often when we talk about randomness, the following phenomena is in our mind. We have a perfectly crystalline lattice. Here I'm drawing you an antiferromagnet located on a lattice, but then it could be that either by choice or simply because the crucible wasn't particularly clean, we are replacing some of the, say, copper ions in a cuprate superconductor by zinc. And then the spin locally disappears and a defect occurs, and we have clearly a random arrangement of sites. A few words, because it will become important. I want to do calculations with you. So a few words about how we would think about describing such a system. What we would do, I mean, of course, yeah, we can also change the bonds, right? We don't need to just put the sites. Then we might have a magnet that is weaker in its bond here and stronger there and elsewhere, maybe as it was before. So the way we would describe this is that now we have a Hamiltonian that depends on, say, randomly chosen, for example, interaction parameters here. This is what Jij stands for. And randomly chosen in a sense that we claim we know the underlying distribution function of this problem. And for any given of those realizations, we can solve the statistical mechanics problem, of course. But this is a function that depends on the individual realizations, of course, and that's not always particularly useful to work with. So what we want to do is we want to, of course, average in some reasonable way. So how would we average? Well, we want to average a quantity that is something that we can sensibly observe, that we can, when we cut the system in half, also is additive in its character, which is not a property of the partition function. It is the free energy, the logarithm of the partition function that has that property that if we cut the system in half, modulus the surface effects, these two individual halves add up to give me the total result if I didn't cut. So therefore, we need to average a logarithm, and this is a major pain. Averaging something is hard. Averaging a logarithm of something is not easier, and has caused generations of theorists to develop this and that theoretical methods with wonderful insights and also significant failures. Good. This is one way to think about randomness. This is the canonical way we should be thinking about it. But we could also look at it from the quote-unquote erbium 166 perspective. Suppose we have, say, a solid that consists of local ingredients where individually, locally, we have a spectrum. So of course, not the nuclear spectrum. It could be due to some internal degrees of freedom in the unit cell, for example. And then we could think what would actually happen when we periodically rearrange the system. And in this system, just like it was for the nucleus, here even more so, I would think, one could indeed contemplate on the idea that even though there's nothing random about the system, an efficient description can be achieved if I did use a random description. The behavior of such a system could be as if it was random, and it's not clear whether such a model would actually be qualitatively distinct from the one we've just seen, where we deliberately changed the periodicity and had individual realizations to average over. On average, at least, there should be lots of similarities. And a last one is something that we were concerned with, which is somehow in between these two regimes, is something that we were concerned about a long time ago. Takes a good old-fashioned 5-4 model that many of you, I believe, have seen in the context of Landau theories or quantum field theories in general of, say, scalar fields. And we add to this 5-4 model a very benign-looking term, something that was proposed initially by Vigamery and Steve Kivitson and Zohan Nusinov. And we add to this a very benign-looking term that's not even an interaction term in the literal sense. It's a quadratic term, but that is non-local in space. Here, the idea was that phi describes deviations of average charge densities, and then you would have to worry about Coulomb interactions. Important is this problem could be analyzed, and we did this 2000, so very long ago, in some reasonable limits, and you can show that it generates its randomness by itself. It behaves if it was random, even though there's nothing here that is disorder distributed. The system generates its disorder distribution on its own right, just because it is uniformly frustrated and strongly interacting. This is a bit of a background how people thought and have been thinking and still think about such random systems. An important development took place a number of years ago, also in the 90s, and it goes back to a wonderful paper by Subir Sachdev and Jean Bouillet. It's the Sachdev-Ige model. I don't want to discuss too much about it. I'm just mentioning we will go to look at a version of it that's more recently been discussed. This is mostly to just give credit where it's due. We have spins that are sitting on some letters, and they're interacting exactly as we had drawn in our first picture. Namely, they're interacting by a random coupling. We have to average over it and so forth. There are certain representations of these spins that allow for a solution in certain limits. We get to this in just a second. Important is we can write down even these quantum models with these random parameters and try to see whether we can learn something that just wasn't there in its principal behavior when we looked at, say, idealized crystalline systems. So the Sachdev-Ige model became very, very popular more recently when Alexei Kitaev formulated a version of it that goes in the name of the now SYK or Sachdev-Ige Kitaev model. I'm giving you not the version that Kitaev talked about, mostly because that's the version we will be discussing. So we have fermions here. They have no dispersion. They just have potentially a chemical potential. But there's an interaction between these fermions that, say, on flavor indices or lattice sites, whatever you wish to understand with these I, J, K, and L. And everybody talks to everybody else here with an interaction that just needs to respect all the properties of anti-symmetry under exchange of, say, for example, 2 creation or 2 annihilation operator. There's a coefficient n here up front. We will see later on why it's been chosen, just to make sense, because there's so many interactions here. This would blow up, and therefore we need to kind of make the typical interaction in each site a little bit smaller if n gets larger and the system gets larger. This is a random variable u here, and it has a mean square deviation of a Gaussian distributed quantity that I call u squared. So Kitaev looked at the same problem just for what's called Majorana fermion, so that's C dagger C. I want to use this version here primarily because it will allow me to look at, for example, superconductivity. why was this so interesting to dive? Well, there were interesting analogies being identified between the fluctuations of this tiny little model and the statistic mechanics of gravity theories in 1+1 dimension. The action of this problem was shown to be identical to the one that we have in a specific gravitational space entered the zitto space too, and we will get to some of this also as we move on during this talk. So now maybe one more comment. Why does this model here have anything to do with that model? Here we have 2 spin operators. Here we have 4 fermion operators. And of course, in the original work, Satchev-Ye used a specific representation of the spin algebra S in terms of bilinear fermionic variables that under certain constraints gives me the correct commutation relationship. So the 2 spins as 4 fermions, and that's what we have here. So this is a bit of this is even a simpler model. So let's look at this model. And what I thought I'd do with you first is, because it's a school, we actually solve it. We really want to see why so many people look at this model, including myself, namely because you can solve this problem rigorously in the limit of n large in about, I believe we will need something like 3.5 minutes. And that's good news. So we have the solution at our hands, and the solution is non-trivial. So this is our model. One more time, we have the chemical potential could be 0 at particle-hole symmetry, so that's not something we are particularly concerned with. It's really a term that has only interactions and is dominated by those. And again, as I mentioned earlier, everybody interacts with everybody else. So you take L, K, J, and I, let's think of sites, 4 sites out of your lattice, and these 4 sites interact, and every quadruple of the n sites that you can possibly find interacts in any possible way with an interaction that is randomly drawn. Now, how do we do the calculations? The first one is we need to average the logarithm. As I told you earlier, that's admittedly a pain, and I believe it goes back to the late Sam Edwards to find an approach to deal with this. Namely, instead of writing the log, we write a function z to the n minus 1 over n, which in the limit of n goes to 0, you can just Taylor expand it, gets you the log back. So therefore, we only need to have some power of n, of z, with a small exponent that we have to average. No, we don't know how to do that either. But suppose the function zn average would be known to us for all integer values, then we can be courageous and say, well, let's just extrapolate this function and 2n goes to 0. That should be fine if this was a polynomial. If we know any polynomial at all the integers, we know it everywhere. Unfortunately, that's not always how it works. Even for this model, this will cause problems, but these problems happen at energies that for this specific model are exponentially small in n, and lots of other stuff happens before this becomes relevant. So we can be rather bold and don't need to worry a whole lot about this replica story for this specific model. There are many models where you should worry a lot more. And that we don't need to worry is something that required hard work. The next, what we are going to do is we write down what is z to the n if n was actually an integer. Or we just need to write the partition function n times. So therefore, all the fields get an additional label that tells me whether this is from the first, the second, or the nth integral. And then I can average over those u's. This is if it's a Gaussian distribution, the averaging is completely easy. Gaussian integrals we can do. And what happens is that whatever you multiply with the Gaussian gets squared. And that's what you see here, right? The time integral over all these variables, I'm doing an action formulation, gets squared. So this is our action after we have averaged it. This is, on the one hand, we paid a high price. Here we had 4 fermion operators, now we've got 8. But the system does not manifestly look random anymore, so we can use the machinery that we have accumulated for non-random systems in many ways. So therefore, we want to rewrite this term here a little bit. So this is a square, you see here. So I can write this as two integrals that are being multiplied, that's clear. And I want to reorganize these sums a little bit. This is not a big deal. This is how it looks like. Let's look at it. I announced already there will be two integrals. Okay, very good. And if I write the sum here and multiply it out, then I'm getting, of course, 4 sums, and that's exactly what we had here. 1, 2, 3, 4. They had to have different indices here to distinguish them. Now we don't need to do this anymore. So that's a very nice looking expression. And now we finally understand why there was these powers of n up front here. Look at this. This term here sums I goes over n variables. So this is of order n. Here we have 4 powers of n, so we better have 3 powers to kill it, so that this is also just good old-fashioned extended in n. And otherwise, this would not make any sense in any sensible thermodynamic limit. That's the problem we have to solve. Fermions that have no kinetic energy and that have this very funny 8-fermion coupling that's non-local in time. I don't have a whole lot of intuition of what this should give me. But of course, the community has accumulated some over the years. So, and that's a very, very clever way of dealing with this, which just we think, oh my God, I really don't want to think in terms of these fermions anymore. I need something that is more informative than just the fermions. And the way you do this is you introduce a constraint. You say, oh, this term of these two fermions that live at different times, it gives me too much chest pain to think about it, so I better write it as something that I call G. Why not? And then I enforce these fermions to be equal to this field G. It's a new field, and it has an interesting property. It depends on 2 variables. It's so-called bilocal. These depend on individually here on each on their own time, but this depends now on 2 time variables. It's a delta function. Delta functions are nasty, so we write the Fourier transform of the delta function. And we need another integral to enforce that delta function. So formally, the integration of sigma needs to go over the imaginary axis, but this will play no particular role in what follows. So what can we do with this trick? We can now replace, if we just multiply the partition function with this 1, no harm is done. But now we have permission to replace these fermions C dagger C by this object G. So therefore, this is gone, and there are no fermions here anymore. The fermions are only here in this term here, that's easy to deal with. And here's a quadratic term in fermions. Quadratic fermion theories can be dealt with exactly. We can just integrate it out. So we do that, and that's what we get. Integrating out gives us so-called trace logs or determinants of log, a log of determinants, and then we get this expression. This is where we see this is the non-interacting problem without the interaction. This is this field that we use to enforce the constraint, and that's our field G that we've just set. So there are no fermions present in the theory anymore. It's only these G's and sigmas, and their names is not taken by chance, because we will right away see that there's something that's extremely familiar to all of us. To do so, we need to recognize that there's this factor n out here in all of these terms that stands out. N and something that's actually independent on n. So our n, the number of sites, has now only appeared as a global coefficient, and here we know what to do. If I have some generic integral, I also called it z, it's for this problem, not necessary. Of course, it's not the same partition function. If I have some integral, I have some function h of x, and there's an n here, and n is large. There's a simple and well-established trick to deal with this. Think of it. E to the minus n times h. When n is large, when h grows and grows, for example, gets larger, then this becomes extremely small. So the integrand is dominated by those values of x where h is smallest, because that's at least the exponent is least damaged and least suppressed. So let's find the value where x is smallest, where h is smallest, and then we can expand around it. So this I can pull outside, and then I have a quadratic expansion because there's no linear term, because it's a minimum. A Gaussian integral everybody can do. I get a result that takes the logarithm, and what do I get? I get basically all I need to know is the value of the function at the minimum, and then there are small corrections to it. So what do I need to do? I need to take this is my S, this is my N, and basically my H is everything that's multiplied with N here. I need to minimize this over the variables that I'm integrating over. I'm integrating over the G and the sigmas. So we can take the derivative of this object. We're almost done. I need to minimize this respect to sigma and respect to G. Let's do the first, sigma. A log, derivative of a log is 1 over, you see that here. And then I have another sigma here, I get a G. So G is this object. And now I realize, of course, it does make a lot of sense to think of this problem as the Green's function, as the non-interacting Green's function, and as the self-energy. And then this is what is the good old-fashioned Dyson equation of many-body theory. On the other hand, you can take the derivative back to G. There's these two terms. One gives you sigma, and the other one gives you G cubed. You need to vary a little bit about the time ordering here, and then you get this G squared G cubed. And that's indeed what you would expect for a self-energy to occur. So what we have accomplished here is an overly complicated way to justify self-consistent second-order perturbation theory. This looks just like the diagram that you would be getting if you just did second-order perturbation theory. Of course, we didn't do second-order perturbation theory. We solved the problem at large n exactly, and there was no limitation on the value of u. It's just that we can feel comfortable with this result, that it at least is not completely insane. Good. Now we need to solve this coupled set of equations, and then we are done. Then we have solved the SYK problem. It's probably more than 3.5 minutes. I would think it is 5.5. So that's what we have to solve. We have this functions. This is a function of time. We assume it only depends on tau minus tau prime minus tau prime minus tau. And then we do the following. We Fourier transform the thing in frequency space, and we guess the answer. If it's interesting, it could be a power law. Why not a power law? So I'm writing a power law here with an exponent characterized by delta, which I want to be positive. The rest here, this minus I sigma omega, is just there to make the system respect causality and so forth. I then use the Dyson equation that we've just established in frequency space. It looks much simpler. And then I realize if indeed this delta here is positive, this is a power that's smaller than 1. Hence, at low frequencies, I can drop this guy relative to the more singular power. So I get G is 1 over sigma. If this is a power law, sigma, G is a power law. I can now Fourier transform G into time space. A power law gives me a power law. Power law cubed gives me a power law. So sigma in time space is a power law. Good news, because I can Fourier transform back and get a power law. So now this whole makes sense only if this and this is equal. So I need to fix the coefficient, which I dropped here because I was lazy, but this is easy. It's just Fourier transformations. And I need these exponents have to match. So 1 minus 2 delta equals minus 1 plus 6 delta. It's a linear equation. Solution is a quarter, right? 1 minus a half is the same as minus 1 plus 3 halves. So we get a quarter and we get all the coefficients and we get a self-energy. Why is this interesting? This is a quantum critical non-Fermi liquid solution that people have been drooling over for decades. And here, all what we've got is 5.5 minutes calculation to get us such a behavior. It was obtained, admittedly, for a model that is absurdly simple. But maybe there's more truth to the ridiculous model than it would appear at first glance. At least what it gives us is some rather funny-looking non-Fermi liquid state. The Fermi liquid is a very exotic state for this model because it doesn't even have a Fermi surface, it doesn't have momentum, and so forth. There's not even a kinetic energy. This is the trivial part of this model that corresponds to some extent to our beloved filled Fermi sea and the Fermi liquid excitations in the extreme opposite limit. But what it gives us is an intuition that is mathematically under some control of extreme strong coupling critical behavior. Now I can use this, I can insert it here, and I can go to the real axis and look what the spectrum looks like, and this is how it looks like. We know usually these spectra are sharp delta peaks. Now what we are getting is this wonderful spectrum, which has a branch cut structure and tells us, yes, there is some resonance there at some frequency here, omega, but it clearly has a character very different from what we would assign to a genuine, well-defined resonance. In this system, clearly this is the case because interaction effects are dominating in this case over dispersion because we set the dispersion to 0. Now, I'm telling you this, on the one hand, we've now learned how to solve such a problem. You can find this in the standard publications. It's a fun calculation to do. I genuinely enjoy it. Important, when I saw this picture here for the first time in a talk somewhere in Karlsruhe during a seminar, I asked myself, what happens when I make this beast a superconductor? So I want to understand, and this is one of the aspects we want to see. I have now a tool that gives me essentially for free something that is extremely hard to obtain in a more honest and more realistic description. It gives me for free a non-Fermi liquid. I want to ask, what happens when I want to pair a non-Fermi liquid? I don't even have the ingredients that I can glue together to the pair as well-defined objects. How can I possibly then make pairs out of them? This was the question that drove us. And at least this little question we could find some answer for. And I will give you a little journey through this analysis for the rest of this talk. Which, yeah? Sorry, I could not understand it. Could you go back 2 slides, please? 2 slides. Is this good or further? One more slide. Yes. Could you remind me in this derivation, where do you take the replica limit and goes to 0? Yes. I have been, assume trivial replica structure. I thought you must not forget this, Joerg, and I did. So we have these are matrices. This sigma is a matrix in replica space, and what we assumed here is that it's proportional to the unit matrix. Then you can take all the limits. Essentially, you don't worry about the distinction between quenched and anneal averaging. This has been shown to be correct, except for energy scales that are exponentially small in n. But you need to independently verify this. I didn't discuss this here. So the replica limit, there is also a little factor n out here that I didn't even write because I'm a bad person. You're welcome. Thank you. Thanks. Very good question. Of course.
Are non-Fermi liquids always associated with quantum critical points, or can they be part of this?
So this model here is critical. It has really only one parameter. Let's stare at it a little bit. This model here, let's forget about the chemical potential. The only parameter of the model is U. So all you can compare is temperature and U, basically. These are the 2 energy scales. At 0 temperature, the system is at this chemical potential value here. It's always critical. You can change the chemical potential. There is a critical phase. And why is this a critical phase? Because the model is silly. But it is at 0 temperature, not a critical point. I believe it can possibly use as a caricature of what a critical point is in a real setting, but the model itself is always critical.
Thank you. Another question? Please go ahead.
Good. Okay, so we have learned something. So then we have my questions again were, can one form Cooper pairs of these incoherent electrons? Also, can one do a little bit more than purely fermionic theories? It turns out that this was needed to answer the first question. And can one physically justify all of this? I'm just giving you equations and solve them and express some pride over this, but does it make physical sense? In particular, the last part will play a big role in tomorrow's lecture. I will focus now a bit more on the first 2. The model we cooked up, engineered, designed, whatever, goes now, this was done with Ilya Estolis back when he was still a grad student a number of years ago, goes now under the name of the Yukawa SYK model. So what we did is we said, well, we have these fermions, they have no dispersion. We add to those Einstein phonons. This is some phonon variable. This is the conjugated momentum. They have the usual commutation relation of momentum and coordinate. And then we couple this coordinate to a bilinear fermion variable. Sorry, I just need to get rid of something here. And there's a coupling constant, and it is this coupling constant that is now chosen to be random. In the meantime, the model has been looked at by other. I mean, there was an independent work by Yusheng Wang, I should mention, completely independently with essentially the same model at around the same time. And it has, in the meantime, also been extended to finite dimensions and much more realistic. Again, this will play a role in tomorrow's talk. Today, we are staying simple. So we have here a random interaction, but now this is basically a random matrix Ij for every given k. And here we have some fermion bilinear. There's no four-fermion interaction. This is the model that we wish to study. The ways to do this, to solve this problem is exactly this. I need to find ways here. Sorry. I need to share. I hope I'm back.
Yeah, you're fine. I mean, we can just
good. Okay. So this is our model, and I still can't change slides. That's my problem here. All of a sudden, hide. I still can't change. Yeah, here. Okay, good. So it's a random number. It will turn out to be important what I do with this random number, because these random numbers have perfect permission to be complex. Then I have to add the complex conjugated, or being purely real. And this can be tuned by a parameter where I'm saying whether the imaginary part has some weight in the distribution or not. And indeed, this realizes different random matrix ensembles as introduced by Wigner and Dyson and mentioned earlier. And I can also interpolate between these two. What we will see is, if these coupling constants are real, I do indeed find that these phonons do what they're supposed to do. They give me superconductivity. If these random coupling constants are purely imaginary or sufficiently large, have sufficiently large imaginary parts, I will find that there is no superconductivity. This is actually interesting. What it means is that now the field here coupled to currents, so basically bond currents in this funny space, and these are odd in time, under time reversal degrees of freedom, which for the system, because spin is trivial, give us no superconductivity whatsoever. That's an interesting independent story to discuss at the right moment. Good. So we find that we can or cannot, depending on how we choose the model, what the model describes, either phonons or coupling to, if you want, so loop current, or we find superconductivity or not. We do the same tricks than before. We introduced a sufficient number of bilocal fields. We had G and sigma already. Now we are forced, indeed, it turns out, to also introduce other fields where we have two creation or also two annihilation operators and the corresponding conjugate field. And that's precisely what you need to do in a description of superconductivity. Finally, we also need to do the same game with our bosons, where we have a boson Green's function and its self-energy to integrate over. It's a fluctuating variable. We get an unpleasantly long expression for S. We take the saddle point on it along the lines that we have discussed. And again, we find something that we can diagrammatically rationalize. In this case, what we get is the good old-fashioned Nambu-Gorkov theory of superconductivity with the normalist Green's function and self-energies, as well as the much discussed Eliashberg equations. So formally, in this limit, you find Eliashberg equations, a set of coupled equations that describe a superconductor. And if you have never heard of Eliashberg equation, that's perfectly fine. Or what we are doing is we're having a field theory with all these fields. We need to solve this problem, this coupled solve problem in the large n limit. And all what is different now is that we have two creation operator and two annihilation operator condensing simultaneously, which is the natural mean field description of superconductivity already pioneered by Bardi and Cooper and Schrieffer. So we have the superconductivity. We can then look at the solution. In the normal state, we again find branch cuts for bosons and fermions, critical behavior. The system is always critical. This is to some extent more surprising because we started off with massive bosons. So why are they critical? In fact, it turns out no matter what the coupling constant, no matter what you do, the fermions always drive the bosons so strongly, renormalize them in such a way that everything becomes critical. And there's one exponent that governs anything. The dynamics of the bosons is enslaved by the fermions. There's one exponent, I called it gamma here. Earlier, this was some version of delta. So power laws pop up all over the place. That's the normal state. So the good news is even this model behaves to some extent just like the SYK model that we had before. We get critical solutions. And then we can see that when we just solve the problem, we need to understand this solution better. We find that indeed the ground state is not a critical state, it's actually always a superconductor. If we choose the interactions of the right sign, and we can look at the spectrum, and the normal state often has an extremely incoherent spectrum. And what we are seeing in the superconducting state is that a gap opens and we get a coherent state. So the first observation is you can find models where you don't even have quasiparticles, but once you give them permission, they want to become superconducting. The superconductor is a perfectly coherent state which does have well-defined Bogoliubov quasiparticles. The coherent weight, the spectral weight of these Bogoliubov quasiparticles is incredibly small. That's how the system remembers that it was a sick object in its normal state. But all this pain and all the diseases that you had as non-quasiparticle state in the normal state are all cured in the superconducting state, which is a fully gapped, perfectly coherent, singlet degenerate state. So bottom line is superconductivity is much more robust than, say, some of the assumptions that underlie the BCS theory as a phenomenon. Yes, this is a very simple model, but it still may make sense to understand it even a little bit deeper, how all of this comes about. As I told you, there's a parameter. I called it alpha earlier. What it meant was of whether I have imaginary coupling constant or real, whether I have phonons or loop currents. We can tune it and we can kill superconductivity. And there's a critical value where this happens, which is of order 1. And then TC actually vanishes in some essential singularity fashion. This caught my attention when we found this because it is known that in these gravitational theories that I've already alluded to you once earlier, that when you break certain conformal invariances or certain symmetries in the problem, you always do this with these very funny essential singularities rather than with power laws. So it smelled like there was some strong similarities with what the gravitational or string theory community had in mind, which was, of course, already the case for the normal state. So therefore, this is now a moment we've seen superconductivity. This is a school. So I felt obliged to step a little bit back and talk about superconductivity. We have 5 minutes left for this one because there want to be a sufficient number of questions. So let me just go on for these 5 more minutes and maybe then we ask questions about everything.
You can take more time to talk. It's fine. You have another 15 minutes.
I see. Okay, well, the best is you just gently tell me, please shut up, Joerg, when I should shut up. Then I don't need to check the time, and I'm perfectly fine either way. So this is a superconductor. We've all seen it. what's so beautiful about it is that we have a giant piece of theoretical physics formulated by Bardi, Cooper, and Schrieffer that basically tells us that pairs are forming and that we have some coherent superposition of pairs that we can write down in the BCS wave function. I'm sure you've all seen this in one form or another. And one aspect, and that's really important, that is underlying the formalism, description, and detailed analysis of the BCS theory is about its normal state. And the normal state is what goes under the name of a Fermi liquid. And that, of course, is this completely ingenious theory, which Sentinel once told me is 21st century theory written in the 20th century by Landau of the Fermi liquid, where we have this conglomerate of strongly coupled fermionic degrees of freedom. And in the end of the day, after the dust settles, all what matters is a scattering amplitude between individual sites, and the degrees of freedom of all the other of electrons that would mutually always interact can be captured in terms of an effective mass and in terms of very, very long lifetimes. I find this absolutely breathtaking, that this does work. And it was one of the reasons why I wanted to study condensed matter physics. So we have this something that looks like a free Fermi gas with an effective mass and a long lifetime, even though there's no reason whatsoever that this should be the case. We look at this problem, and then we do what the German likes to do, which is accounting. We just count how many degrees of freedom we have, and this you can always do when you have the entropy. And when you look at these degrees of freedom characterized by the entropy, you can essentially make enormous number of predictions. For example, you find that the heat capacity behaves like a heat capacity of free electrons. It's only affected by the mass renormalization. The charge responses gets enhanced and has a Stoner factor, if you wish so, and so forth. Everything is fine. These are almost perfect quasi-particles. Why is this important? When we want to have two electrons to form a pair, we need to calculate its pair correlation function. And for free electrons, or something that behaves like free electrons, there's a logarithm popping up here, the pair susceptibility. It's an easy calculation. It's just two integrals of momentum and frequency. You find it's a log. And the log is born from the ideal electron character of these Fermi liquid characters. If I now sum up lots of those pair with some weak interaction, I find this result. I ask when does the susceptibility diverges, and since there's a log, I get the famous Cooper instability result that given this pairing interactions, I now find some exponentially small but finite transition temperature. That's why Fermi liquid theory is so important. Now, what is interesting is when you have these critical points, and we just had toy models for critical behavior, you actually have very strong reasons to believe that there are no good quasi-particles. That in fact what happens here is that masses diverge and that lifetimes are extremely short, and that particles are no longer have an integrity as if they were well-defined objects, but they are basically becoming some entangled soup. And these degrees of freedom, we need to repeat our analysis, check whether we can do the same Cooper analysis that was done before. And this was done, in fact, in the 90s by incredibly smart colleagues who said, well, let me just assume that I have these very short lifetimes and repeat the calculation. And because the electrons are ill-defined, I don't get my log anymore. Nothing is divergent because of these funny power laws. And now what I would have to get is an interaction that is stronger than some critical value. And only when this is the case, then I would get superconductivity, because this kills the log. It's not a hard calculation, it's rather easy to see. This is surprising because superconductivity should somehow be the exception, just like ferromagnetism, rather than the rule. And experimentally, when you're near these quantum critical points, and I'm showing you very, very different materials, from iron-based superconductors, heavy fermions, all the way to organic charge transfer salts. And in all of them, you see some superconductivity near something where you have a second order line going to zero. So This could all be accidents, but it could also be that there's a deeper question behind, that near these critical points, superconductivity is abundant. And the way to think about it was basically done in two very, very different lines of reasoning. The one argument was superconductivity by critical bosons near such a critical point, like the ones we've had in our SYK model, need to be done carefully. And if you look at this, yes, you get these long lifetimes, but you got to be careful. These long lifetimes don't come for free. They also give you a highly singular pairing interaction. And what this calculation here that gave us this constant was doing is it assumed that the pairing interaction is still the same, instantaneous and non-dynamical. Instead, the pairing interaction is highly dynamical and governed by the same power laws as we have, for example, seen in our SYK model. And this was discussed in a number of wonderful works over the years. So the pairing interaction also gets dynamical. Once you do this, you have a better chance to capture superconductivity in this problem. And then there was the second line of reasoning that goes under the name of holographic superconductivity. And in the second line of reasoning, the following statement was made. You can map a critical problem, a critical field theory in d+1 dimension onto a classical gravity theory in d+2 dimension, and then everything will be good. And these are wonderful words done by incredibly smart people. I just never understood a word of what it meant. And what I want to show you in the next lecture, in the first half of it, is how these two phenomena actually come together. I want to convince you that I can form an explicit, concrete, and a quantitative mathematical map between an electron phonon problem with critical bosons and a quantum field theory that sits in an extra dimension and where we have essentially a Ginzburg-Landau theory in a curved space. And we will see where the curvature comes from and why there's an extra dimension. That will be our goal for the next lecture. And if I understand things correctly, this would now indeed be a good moment for me to pause and maybe ask you to give me some additional questions.
If you have a question, you can just come to the front and speak into these mics because that's how the Zoom recording works. Yeah, Oscar, go ahead. Could you speak into these mics?
Thank you very much for a wonderful lecture, Joerg. I have a question regarding the superconductivity in the SYK, where, if I understood correctly, you start with no dispersion whatsoever in the chemical potential as well as return, and then this random comes up to ozone. What sets the typical stiffness in that case? Is it just increase or
You mean the superfluid stiffness?
Yeah.
Yeah, so that's a brilliant question. Thank you. Thanks, Oscar. What we are doing here in the model that I've presented to you is a model of, if you wish, to zero-dimensional problem or infinite dimension, it doesn't matter. But you can look at it, it has no spatial structure because everybody coupled to everybody else. So I did a mean field calculation. But this mean field calculation does not know the concept of a stiffness. It has no knowledge of it. A stiffness, again, is what I have is I have a superconducting order parameter. It's got a phase. What I want to accomplish is if I twist the phase here, whether the phase far away from it responds to that or not is loose. If there's no concept of close and far, I cannot describe such a stiffness. Of course, we thought about it. All these concepts that this model does not have the concept of stiffness. What we did do is we generalized the entire scheme to higher dimensions. Then you can very well define stiffnesses. In this case, you do find very interesting behavior, namely that in these extremely incoherent systems, you have a much reduced stiffness. But this model, as I presented it to you, doesn't know anything about stiffness. But you can naturally generalize the model But for this, you first need to give the lecture on the non-generalized case, which is what I've done today. Tomorrow, I can show you pictures for stiffnesses that come of generalization of the same model in higher dimensions. And then we can see how the still existing incoherence of the system, the still existing non-thermal liquid behavior of these systems affects the stiffness. Yeah. So, I mean, there's Vlad Dobrosavljevic sitting up front, so he knows all of this much better than I do, because he has done it in more cases than I have. In these models, mean field models as we have them here, what you do is, there are two ways to deal with this. One is you look at, you have a certain solution. The solution that we looked at here was replica symmetric, no replica symmetry breaking. Then you look at the fluctuations around this solution and look at the eigenvalues of the fluctuation matrix and check whether it has negative eigenvalues. If it does, clearly you're sitting on an unstable solution. And as I mentioned, this is indeed the case here, but the eigenvalue that is negative is exponentially small in n. And there are power law corrections at finite n that are even more important in my view. Another way of doing this is you just break the replica symmetry by hand. And then there are famous guesses that go back to Brayan, Moore, and Parisi. And if you do so, then you find typically solutions that are more stable. But I think you need to actively ask and look for it. But there's an entire machinery, and this was done for this problem. I have just completely brushed this under the carpet.
So I have this question. You emphasized that this is resulting randomness in this model, and I understand that Subir and his collaborators are now pushing the view that all this strange random stuff is only due to randomness. But there are theories which have a very similar structure, some DMFT theories which also have a local self-energy, which is known to determine by a nonlinear equation, which you can imagine that there are other models without randomness that could give rise to the same structure. So what's your view on this?
So of the calculation that I can do, I only know random models that give me convincingly linear resistivity at critical points. That's the answer as far as calculations are concerned that I can actually do. Do I believe? Could it be that that there is a different principle at work that makes equations look like the ones that we obtain from randomness? So some other mechanism that basically drives the system being local. That could be. I would personally always expect it for clean systems to be unstable ultimately. But this could well be also in reality the case that there is no linear resistivity down to lowest temperatures in real systems because there's always superconducting. We know it's not quite like this, but also real systems are typically random. What I will be talking about tomorrow is in fact an attempt to describe what goes under the name of the strange metal phase in overdoped cuprates. But again, we will use randomness in order to explain it. I have no good idea how you can make it work without randomness. But that's just maybe it's just my shortcoming. I don't know.
Very well. Question from Andre.
Randomness in this case, it comes from the order or from where?
Does the randomness, does the randomness come from this order or from something else? That's the question.
So in the explicit calculation that was done, randomness was quench randomness given that you average order. It would then naturally come from this order. There are models that were written down by Ed Witten that are non-random that give the exact same equations. So therefore, it comes from frustration of certain matrix models. The one model I showed you very briefly, where we looked at self-generated randomness, we had a model that had no randomness whatsoever, but you could show basically the following. Add to this model an infinitesimal random field. Do the calculation for a random model, do your replica symmetry breaking, check for it, you find replica symmetry breaking. And then you ask the question, does that survive the zero randomness limit at the end of the calculation? And there are models we found where you actually have glassiness surviving the zero randomness limit. But of course, you need to look at it just like when you look for ferromagnetism, you need to add a field. You break the symmetry. In this case, it's not a symmetry, but it's a replica structure. In the limit of, say, zero field, you get a ferromagnet. In the limit of zero randomness, you get a random system. Those models do exist. Those were not the ones that I've discussed here, because these calculations are just a lot harder to do.
Basically, in your mind, you just talk about applying it to the overlap with
Yes.
case will come from sources from what?
Yeah. So the statement that I will make tomorrow about the overdope poop rates is that there would be a Fermi liquid if the system was perfectly clean. But the disorder effects that will drive it to a phase that is over a wide regime of parameters characterized by a marginal Fermi liquid state due to scattering of Andreev scattering of local superconducting islands.
One last quick question from Una. See the next speaker.
Hi, Una. Yes. 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 So I think this is absolutely awesome question, because what I will do is I will say in my next lecture tomorrow, as you remember, Una told us that what I'm telling you here is that the randomness is an interaction effect. How can I get to this? And I will give you examples for this. It's just easier if I do this in this way. So for example, when you have a perfectly clean electronic system that scatters off systems that have that are random, local two-level systems, local superconducting puddles, you would always map it onto a problem where the interaction is the random object, not the single particle potential. It may or may not be, but that's not even important. So the most singular scattering is then of the interaction kind. But this is very irritating if you look at it from the perspective of, for example, only fermion-fermion problems. It looks rather unnatural. It looks very natural in the problems that I will discuss to you tomorrow. So there's not a fair answer, because I'm not giving you the answer. I'm telling you to wait until tomorrow, but I think it will be more convincing then. And also this way I don't cut into the next speaker's talk.
Which is Una.
I know.